I think we can start. So thank you for being here. This is the third session of this second season of the Journal Path. And today's speech will be given by Steve Azzolin. He is a master's student at the University of Trento in AIS, Artificial Intelligence Systems. And the talk will be about double explainability of GNNs via logic combination of kernel concept.
Thank you very much, and thank you everybody for the invitation. This is actually my master thesis, which was co-supervised also by Antonio Longa, and which ultimately led to an XLR paper. So thank you also to Antonio, which, I mean, part of the merit is also yours. A little bit, a small part. And so my idea for today's talk is to start gently motivating why we should study graphs and to some extent why graph neural networks are cool. I will try to convince you on that, so you will let me know if it works. Then I will try to motivate why we need to study explainability in deep neural networks and why it is a hot research topic. Along with that, I will try to give a brief overview of the current state of the art in explainability for GNNs, and this will lead to our contribution and finally to the results. Do you hear me? Shall I speak louder? So, to start, you might be aware that graphs can be found almost everywhere. We can see them in biological and chemical applications. Molecules and proteins are often represented as graphs. Then we can find graphs also on applications like social networks or the analysis of brain data. I know that in the audience there are many people working on computer vision and NLP, and so to give a more practical example, we can even consider an image like a graph. We can, you can apply your favorite superpixelation algorithm. Every superpixel corresponds to a node, which are then connected via edges based on their adjacency. On the same vein, there is a quite famous task or dataset, depends on your point of view, like the visual genome, which allows you to find objects or people in certain images and connect them together via relations, ending up with a graph. Also, text is notoriously can be notoriously represented via graphs in different ways depending on the task that you have at hand. So, to some extent, we may say that well, everything in a word is a graph if we want to bring this to the extreme. So it makes sense, right, to develop a specific architecture to deal with this type of data. When we deal, for example, with tabular data, fully connected networks work as well. For images, convolutional neural network can specifically exploit the inductive bias of translation equivariance. And for recurrent neural, and for language or sequence-like applications, recurrent neural networks were much used, at least before the explosion of the transformer. Actually, a small spoiler why GNNs are kind of cool is that you can show that in some specific circumstances, transformers are graph neural networks, especially when, if you consider a graph neural network and a fully connected network, then you can really have this sort of equivalence. I found it quite interesting. At this point, I hope that nobody will complain for that, but I decided to steal a couple of slides from Petar Velikčović, that for the people, for those of you who don't know him, is a staff researcher at DeepMind, and I would say that he's one of the leading scientists in the geometric deep learning field. And so, to start with a couple of provocative slides, we may say that in many ways graphs are the main modality of data that we receive from nature. And the second one, maybe more provocative, is that graph representation learning is likely critical on the path to AGI. Of course, for today's talk, I think it's enough to talk about AGI and these big claims, and so I would say that we can go back to something more practical and to something more boring. We can have a look at some equations of how we can define a basic graph neural network. So, if we assume to start with this toy graph with 4 nodes and 3 edges, we assume that we have at our disposal a feature vector x for every node, and we can start our computation by initializing at the first iteration the embedding for every node with the initial node features of every node, and then at every iteration we perform the following propagation rule. Considering node B, for example, the red one, we start by aggregating together all the information of the nearby nodes at the previous iteration, aggregating them with an aggregator function A, which can be implemented, for example, via min or a sum. Then, once we have obtained this aggregated representation of the nearby nodes, we can perform an update operator in order to combine the nearby information with the current node's information. Note that despite this apparent simplicity of this formulation of graph neural networks, there is actually a great deal of research going on in designing powerful and expressive A and U operations. So there is a big deal going on under these two functions. At this point, after a sufficient number of iterations, we end up with a refined set of node features, which can be used, for example, for performing node prediction tasks, for example, by attaching a classification head on top of every node, or we can perform some prediction at graph level, so considering the entire graph as a single entity. And this can be done by aggregating all together the final embeddings of every node via an aggregator function P. Again, there is a great deal of research going on in studying expressive and powerful aggregator function, because applying a simple min or a simple sum, will destroy too much information, let's say, put in a simple way. But of course, for today's talk, I will stop here in order not to spend too much time in the description of the GNN framework. But by the way, if you have any question, feel free to interrupt me at any time. Then let me spend a few words why people study explainability. Well, we all know that neural networks are very powerful and they solve a lot of tasks. However, probably we know, some of us know, that the predictions are difficult to be interpreted and that it's not really clear what's going on in your network, right? So you give your sample that you want to classify, and the network spits out the results, and that's basically all we get. However, it is well known that in this way, the fact that we are not really able to understand what's going on may lead to some problems. For example, in this tonight's paper, it has been shown that the network, in the first case, just looks at the presence of the watermark in order to predict a specific class. And when you remove the specific watermark, then the prediction is no more correct. This is not the correct behavior that you would expect from your network, right? And a similar behavior happens in this other example, in which the class wolf is predicted just by looking at whether there is no around the wolf, and instead of looking at specific characteristic like of the nose or the eye of the wolf. And so again, it's not the behavior we would like to have. Luckily for us, some methods have been proposed to try to shed light over this behavior. For example, line, integrated gradients, and CAM. Here a complete list will be too long, and they help in somehow debugging neural networks, but we are not quite there at fully understanding what's going on inside the network. At this point, let's see what's going on for graph neural networks, where GNNs are black box too, unfortunately. However, as for non-graph architecture, methods have been proposed to try to understand something about the network. In this taxonomy, we can identify two main branches. On the left, distance level explanations, and on the right, model level explanations. Before going deeper into their differences, let me spend a few words about the differences in explainability for standard images and for graphs. If you have ever worked with images, you might be familiar with this kind of representation. It is a saliency map which highlights which part of the input image contains the most informative or the most important parts of your input image for a certain prediction. We can't really have the same for graphs, where we instead rely either on attribution scores which are assigned to specific nodes or to specific edges. So in this case, darker colors means higher importance. So yeah, to go back, the two different branches of our taxonomy, we can start by instance level explanations, which return exactly what I've shown before. So an important score either to a single, to every node or to every edges. They are called local or instance level because they really give an explanation for every sample that you provide. So if you want to classify a certain image, you will get as a result the representation on the node or on the edges that I showed you before for this specific instance. There are many subcategories like gradient-based, perturbation-based, decomposition, and surrogate-based. If you are somehow familiar with some notions of explainability for convolutional neural network, for example, you may be familiar with some of the algorithms in the gradient-based category. The reason is that they are often based on backward gradients, and they are thus very general and applicable to a wide variety of architectures. While instead the others like GNN Explainer or GLGExplainer have been proposed to specifically deal with the graph domain, which poses its unique challenges somehow. For what concerns model-level explanations, instead, they are aimed at capturing the global behavior of the network as a whole, trying to abstract individual noisy local explanations. Well, before our contribution, there was just one approach, which is called GNN. However, small spoiler, we're going to present our GLGExplainer in a few slide time. At this point, you may wonder, okay, but why are we studying global explanations? What's the deal with that? The reason is that, as you can see, global explainers are seldom studied, and in addition, mining local explanations is surprisingly hard, in the sense that you may have one or more local explanations for every input sample, and so if you have a huge data set, you would end up with a huge amount of local explanations to be inspected, and that's too much. In addition, they are often noisy, and their quality is often difficult to be evaluated. And so we believe that a summarized view, a global view, is amenable to a more prompt debugging. I have a couple of slides summarizing how its GNN or competitor works. I don't want to go into the finest details of this approach, but let me just say 2 words. It is based on a reinforcement learning-based graph generation problem, which generates as output a synthetic prototypical graph, which is aimed at summarizing, let's say, a specific class. So, for example, here we have a bunch of graphs that all share a specific substructure, and in the end, hopefully, this algorithm will spit out something like this, which corresponds to the commonalities in our dataset. However, this approach leaves a couple of open challenges. For example, the approach requires the definition of a set of graph rules which are put in place in order to ensure that the generated synthetic graphs is faithful to the domain we are working with. Because, for example, think about molecules, you must fulfill some of the fundamental rules of chemistry. So, for example, 2 atoms cannot be connected together, and so it is pointless to generate such a prototypical explanation. And so this approach requires the definition of such graph rules. However, they are difficult to be gathered and also difficult to be implemented. Despite the presence of these graph rules, the algorithm is still not guaranteed to provide as output a graph which fulfills all of them. And so this brings us to the description of our proposed approach, which is named Global Logic-based GNN Explainer. In short, our approach can be summarized by this sketch. We have our GNN that we want to explain, and that has been trained on a specific data set. At this point, we extract a bunch of local explanations by means of any of the available local explainers that we have seen so far, and then we feed all those local explanations to our explainer. The system is trained with the only direct supervision coming from the predictions of the original GNN that we want to explain, in such a way that our method, our algorithm, tries to emulate the predictive behavior of the underlying GNN that we want to explain, and provides as output a bunch of logic formulas which are summarizing the predictive behavior of the model, as we will see in a moment. This is a more detailed view of our algorithm. I will try to walk you through this picture. So to start, as I said before, we have our GNN that we want to explain and our data set, and we extract a bunch of local explanations with any of the available approaches that we saw so far. We apply some thresholding, some binarization in order to get rid of the less relevant part of the input graph. So for example here, if we have this graph with an house, with a grid, we will delete all the other edges, and we end up just with these two motifs that are relevant for the final prediction, as we will see in our, as we will see later. At this point, what we want to do with this local explanation is we want to learn an embedding over those local explanation, and this is done via graph neural network, since it's the de facto standard for learning representation of graphs. And while we create this embedding, actually, we train also a bunch of prototypes which are initialized randomly at the beginning of training, and which are learned along with other parameters of the network. Some losses are put in place in order to push those prototypes to align as prototypical representation of those clusters of motifs. So, for example, prototype 1 will correspond to the cluster of grids, and prototype 3 to the prototypes to the cluster of houses. One of the most important parts in this architecture is the one responsible for the extraction of logic formulas, which is the one at the bottom right of the picture. It's called GLN, which stands for Entropy-based Logic-based Network. It works by taking as input a vector of concept activation, and it provides you a set of a bunch of logic formulas summarizing the behavior of the model. And so we need to go from an embedding space of graphs to a vector like this of concept activation. And we do this passing through a vector of prototype activation, which simply computes, for example, the inverse of the distance from every sample to the prototypes, in such a way that we will have a higher value for the prototype closest to each sample. We apply some discretization sampling in order to get, in the end, and to move from the initial graph domain of local explanation to the final vector of concept activation. Let me spend a few more words about the learning of the formulas. Here we apply a discretization step which promotes the discreteness of the formula, which makes them more interpretable, and promotes also the alignment between the entropy layer and the multilayer perception. Here there is like a lot going on inside here. I decided not to go into the very fine details of it because it will take a lot of time. But in case you are interested, or you have many, or you have any questions, feel free to ask. I'll be happy to answer them. So yeah, the entropy layer, just to give you an idea, is nothing but a fully connected layer, just with steroids, in the sense that it applies an internal entropy regularization for concept selection, and in addition to that, it builds an internal truth table which will be used to build and to construct the final logic formulas. The losses that we use for training our system is a surrogate loss in order to emulate and to somehow replicate the predictions of the original GNN, plus two clustering losses in order to promote the clustering of samples around every prototype. Note that we are not applying any supervision on the concepts, which are learned somehow in a supervised manner. So we are simply saying to the network to cluster samples together, but we are not saying which motifs in this example should be the. I think we can have a brief look at some of our results. To start simple, we can consider a synthetic data set, which is built with these four basic ingredients: a random Barabasi Albert, which is nothing but a random graph generator, and a house motif, a grid motif, and a wheel motif. The class 1 of our dataset is composed by aggregating together the random Barabasi Albert plus any combination of two of the other motifs. So, for example, house and grid, or house and wheel, or grid and wheel. One inside class 0 is built just attaching one single motif or all the motifs together, or no motif, the last one. Of course, we need a GNN to explain. In this case, we use a simple GCN, which is arguably one of the simplest GNN models. We train over the synthetic data set, and we obtain the fairly good results. And in the end, it's a synthetic toy data set, so fair enough. However, despite the high performances, if you have a closer look at the distribution of the accuracy for the different combination of concepts, we see that every sample which contains all the motifs together is never correctly predicted. And so we expect these to be reflected also in the final logic formulas. So keep this in mind. If we run our competitor GNN, it provides us something like that. For class 0, it does not converge, it simply returns a single isolated node. So basically, it is telling us nothing about the graph neural network. And for class 0, for class 1, sorry, it's providing something, but it doesn't really look like what we have seen. Like, so the house motif, the grid motif, just the first one, but it is not really shaped like our wheel. So somehow it is explaining, I mean, it is providing us something that does not belong to the initial input domain. Our system instead provides these logic formulas. They don't seem really interpretable right at first glance, but remember that we have at our disposal an embedding and a set of prototypes, and if we inspect them, we see that indeed the prototypes do align as prototypical representation, and some clusters do emerge. Here, the different colors correspond to the different shapes and to the different motifs. So what we can do is to simply replace here the formulas DP with one of the motifs sampled from this embedding space in order to get something more visually friendly, let's say. And so for class 0, the final formulas corresponds indeed to the definition of the data set that we saw before. So the model is predicting class 0, for example, when the model sees a wheel or an house or a grid or the empty Barabasi, the random Barabasi Albert graph. Instead, for class 1, again, correctly captures that there must be two motifs together for the network in order to predict class 1, but as you can see, there is also the case in which there are all the three motifs together. And this is related to the fact that the GNN was never correctly predicting this scenario as belonging to class 0, and indeed the formulas is telling us that this scenario belongs to class 1, and so somehow you can debug the network understanding that this scenario is indeed corresponding to the wrong class. To conclude, I would say that our contribution is the first global explainer for GNNs, which is able to provide logic formulas for describing the behavior of the model. It is more informative than the previous state-of-the-art, and it is inherently faithful to the data domain, thanks to the fact that we are using local explanations as input to our explainer, instead of generating a synthetic graph with a reinforcement learning algorithm, for example. And we also developed a supervised algorithm for concept discovery. There are more results in our paper with other data sets. However, for the sake of time and this presentation, I kept them off. But if you are interested, I'm happy to answer any question, and also you can check out the paper if you're interested. And yeah, the presentation is over.
Let's thank the speaker.